So we saw in the last set of videos that we can go through and try to approximate the limit using a table of values, but that doesn't always give us an exact value. So one way to get an exact value of a limit is to utilize the analytic methods. And we're going to use the same analytic methods that we used in Calculus 1. So factoring, adding rational expressions, direct substitution, those sorts of things. And we're just going to look at the techniques, and hopefully this will remind you of some of the things you did in Calculus 1 to evaluate the limits analytically. So we have this first limit, xy approaches 6, 3, of our function fxy, which is going to be xy cos x minus 2y. Now the first thing that we always try, no matter what, is direct substitution. So that's going to be 6 times 3 cos of 6 minus 2 times 3. By just doing some simple evaluation, that gives us 18 cos of 6 minus 6, which is 0. And then remember that the cosine of 0 is 1, and 18 times 1 is usually 18. Alright, so that's a really easy example by using direct substitution, which should be our first line of defense. However, in the next three examples, we're going to see that direct substitution fails us. Alright, so over here, we try direct substitution of 2, 2 into this expression x minus y, x squared minus y squared. So that's going to give us 2 minus 2 divided by 2 squared minus 2 squared, which is 0 over 0. Alright, and that's not good. In Calc 1, that was an indeterminate form, but we don't have that L'Hopital's rule in Calculus 3. But we can perform some algebra. So what we're going to do is we're going to rewrite this. So we're going to have the limit as xy approaches 2, 2. And the numerator is prime, we can't factor it, but the denominator is a difference of squares, x plus y, x minus y. We can cancel out the x minus y's, and now we can rewrite this as the limit as xy, x comma y, approaches 2, 2 of 1 over x plus y. We try direct substitution now, and we end up with 1 over 2 plus 2, otherwise known as 1/4. Of course, we can verify this using a table of values. However, this is much more efficient and also more accurate, because then we don't have to guess as to what's going on from both sides, or all four sides in this case. A third example. Limit of xy approaches 1, 1 of 2x squared minus xy minus y squared divided by x squared minus y squared. So once again, we try direct substitution. Most of you can see where this is going automatically. So 2 times 1 square minus 1 times 1 minus 1 square divided by 1 square minus 1 square. Immediately we see the denominator 0. 2 minus 1 is 0 again. Alright, so direct substitution does not work. So what we are going to do is we are going to factor once again. Now the numerator is a little bit trickier, but not too bad. So we have lim of xy approaches 1, 1. To factor 2x squared minus xy minus y squared, we know that we're probably going to have a 2x and an x to build the 2x squared. We're going to need a y and a y to build y squared. And then we need to get to negative xy. So that means we should put the negative opposite of the bigger x. All right, so I'm going to put a negative in between x and y, and a positive between 2x and y. And of course you could FOIL that out just to verify. It should work. In the last example we saw the difference of squares. So we can factor this x squared minus y squared into x plus y, x minus y. And now we get some good news because the x minus y's cancel out. And now we can try direct substitution. So by direct substitution, that's going to give us 2 times 1 plus 1 divided by 1 plus 1, which should work out to be 3/2. Okay, again, much more efficient than utilizing our table of values. One final example, we have the limit as xy approaches 4, 4 of root x minus root y divided by x minus y. Now we know that we can't factor this. So we would try direct substitution, of course, first. And by direct substitution, I think it's pretty obvious that this is going to give us a 0 over 0. Alright, so we get 2 minus 2, which is 0, 4 minus 4, which is 0. So it is unfortunately going to be not a direct substitution yet. One of the techniques you might remember from Calculus 1 is that if you have radicals, you can try to rationalize the expression. And in this case, we're actually going to have to rationalize the numerator. So I'm just going to work on the algebra for this. I'm not going to do the limit or write the limit out. And you might remember to rationalize, what you have to do is you have to multiply by the conjugate. And the conjugate is just a fancy way of saying change the sign in the middle of the radicals. Okay, so the conjugate, you just change that around. Okay, so now we have root x plus y, and we're going to multiply by root x plus y. All right, so you have to multiply the top and the bottom by the same thing. Now the trick was in Calculus 1, you would FOIL wherever there were radicals, and then wherever there were not radicals, you would keep that the same. All right, so let's just keep the denominator as x minus y root x plus root y. All right. However, the numerator we are going to have to FOIL. So root x times root x, that's root x squared, or just x. Root x times y is going to be positive root xy. Negative y times, or negative root y times positive root x is a negative root xy. And then finally, negative root y times positive root y is just going to turn into a y. And you might be thinking, well, this looks completely worse than what we started with. However, what you'll notice is that the conjugate produces opposites of those radicals. And that's the beauty of the conjugate, is that it always produces those sorts of cancellations. Okay. And so, again, we still have the algebra. We're not dealing with the limit yet. We have x minus y in the numerator, quantity x minus y, root x plus y in the denominator. The x minus y's are going to cancel, and now we can apply the limit. So now this turns into the limit as xy approaches 4 of 1 over root x plus root y. Or in other words, by direct substitution, that's going to be 1 over root 4 plus root 4. 2 plus 2 is 4, so we end up with 1/4. So hopefully this gives you an overview of some of the techniques that can be utilized to be able to evaluate these sorts of analytic methods for finding limits. One last video in this section we're going to look at next is being able to determine when a limit does not exist.